So, our today's guest is Adam Ingram from Newcastle University in United Kingdom. And he is a lecturer in astrophysics and Royal Society University Research Fellow at Newcastle University. His main research field includes observation and theoretical modeling of modeling to probe the environment of accreting black holes. And for the people who are very familiar with the field, Adam has developed several modules to model timing and spectral observations from the XRBs, X-ray binaries. And Adam did his PhD from Durham University in 2012. And for that PhD, he got Michael Penston Award for Best Thesis in 2012. And he, after his PhD in 2012, he moved to University of Amsterdam for his first postdoc. And later he got prestigious NWO Venny Research Fellow Award for 2014-2017 before he moved after he moved to Oxford University for his University Research Fellow position. And very recently in 2021 he moved to Newcastle University in UK. So many thanks, Adam. You accepted our offer to give a seminar at SAAO. So please, thanks a lot, and please start your presentation.
Okay, great. Thank you. Thank you for the introduction, and many thanks for inviting me. So first of all, here's a big list of my collaborators. I'll probably show most work by Gulo Mastroserio, who's the first name on here. He was my PhD student, along with Michiel van der Klies, who's the main supervisor back in the University of Amsterdam. He graduated a while ago now, and he's working in Caltech with Javier Garcia and also Erin Kara in MIT. So we have a collaboration going where we're doing this X-ray reverberation mapping stuff. And then there's also my two students who are still in Oxford, Amy Knight and Ed Nathan. So they've all contributed to this. So basically, I'm interested in accreting black holes, and I'm interested in accreting black holes in these two very different scenarios. So on the left is a black hole X-ray binary, where we have a black hole that's around about 10 times the mass of the sun, and it's accreting gas from its binary partner. And on the right is a much, much bigger black hole, a supermassive black hole that's millions to billions of times the mass of the sun, and it's accreting from its entire host galaxy. So even though these scales are dramatically different, the theory and the hope is if you get close enough to the black hole, basically the same thing is happening. The material that's spiraling towards the black hole is heated to such high temperatures that it glows very brightly in X-rays. So if we kind of look at these things with an X-ray telescope, we're seeing a signal that's coming directly from this region with a uniquely strong gravitational field. So if we try and zoom in and work out what's going on in the inner regions, what does it look like? We can't image these regions in any of these very X-ray bright objects. So we can only infer. We know that there has to be a disk, some kind of geometrically thin, optically thick disk. And we also know that there needs to be some cloud of hot electrons close to the black hole, which I'm going to be calling the X-ray corona. And I'm going to try and be as agnostic as possible about the shape and nature of this corona. So I'm drawing it here as a kind of a donut inside of a truncated disk. This is called the truncated disk model. And I've put a rough estimate as to the size here, 2 to 40 gravitational radii, might be a little bit bigger, might be a little bit smaller, but it needs to be relatively compact in terms of, like, you know, the size of the whole system. And a gravitational radius is on the top right there. It's half a Schwarzschild radius. But you know, part of the problem here is we don't know exactly what the corona looks like. So it could, for example, be something that's more compact at the base of the jet, or you know, pick your own geometry. I'm going to try and be agnostic throughout, but we need to solve this eventually if we want to kind of make progress. So when we look at the spectrum, there are three main processes that contribute to the spectrum. The disk is thermalized, so you get a thermal spectrum from the disk. Peaking a very different wavelength for AGN and X-ray binaries. It's UV in the AGN and soft X-rays in the X-ray binaries. And And then you also have this blue spectrum here, this blue power law with a high energy cutoff and a low energy cutoff. And this is what we think is coming from the corona. And we know this has to be something to do with Compton up scattering. The electrons in the corona more energetic than the photons from the disk. So when photons from the disk have collisions, have interactions with the electrons in the corona, they gain energy each time, and that gives you this power law. The high energy cutoff tells you about the electron temperature, because the electrons can't give more energy to the photons than they actually have. And the low energy cutoff tells you about the seed photon temperature. Okay, so there's also the kind of the most important the most important component for the purposes of this talk is the reflection spectrum, this green line that you see here. So basically the corona is irradiating the disk, and all of the flux that goes into the disk is eventually reprocessed and comes back out again with a different spectrum. So really this is a radiation and reprocessing, but we always call it reflection, and I'm going to continue to call it reflection, but it isn't really reflection because the emergent spectrum from the disk has a different spectrum to the irradiating spectrum. Okay, and crucially in the rest frame of the disk, it's the gray line that's being emitted on this plot. So you see there's all of these narrow fluorescence lines, the most important one being ion K alpha at 6.4 keV. There's also an ion K beta there. And then you see edges as well, absorption edges. And there's this big feature at about 20 to 30 keV. This is called the Compton hump, and it comes from inelastic Compton scattering. So that the most energetic photons do get scattered, they just lose a lot of energy when they do so. So as the observer at infinity in our solar system, we don't see the gray line, we see the green line. And that's of course because the material in the disk is orbiting rapidly around the black hole. So you get Doppler shifts and Doppler boosting from that rapid orbital motion. And then you also get gravitational redshift, right? So photons, in order to get to us, they have to climb out of the gravitational potential well of the black hole, and they lose energy in doing that, so they get redder. Okay. Another thing that's going to be really crucial for this talk is that the rest frame reflection spectrum itself critically depends on the ionization state of the disk. So for this example here, the disk is basically all bound atoms, very low ionization state, which is what would happen if the irradiation was at a very low level. If you cranked up the irradiation and made this disk very ionized, you get something that's completely different. All right, so you see there's many more lines here, and that's because there's lots of ionic species now present, and each ionic species has different transition energies. There's also many more free electrons for electron scattering. It's just a lot more complicated, right? So throughout, we're calculating this using Javier Garcia's model, Silva. So this self-consistently calculates the ionization balance in the disk. So the actual ionization is in a very complicated calculation. But the leading order kind of parameter that you put into the model is this ionization parameter on the bottom right here. And this is basically, it's proportional to the irradiating X-ray flux divided by the density of the disk. And that kind of makes sense, right? Kind of how heavily ionized the medium is something to do with the number and energy of the photons that are coming in and the number of ions that are there, or the number of atoms that are there to ionize. Okay, so this is something that's gonna keep on coming up, so remember it, right? Okay, so we've introduced enough to have an overview of the talk now. So basically, what I want to talk about is trying to use this X-ray reflection signal to do two ambitious and cool things. One is measuring black hole mass, and the other is even more ambitious, maybe even crazy, I don't know, measuring the Hubble constant with AGN, right? So, I mean, it's been an obvious thing for a very long time that if you can measure the distance to AGN, it's easy to measure the redshift, so therefore you can measure the Hubble constant. So maybe we can try and do that. And the tool that I want to talk about to do this all with is X-ray reverberation mapping. So what's this? Well, the reflected emission, not only does it have the energy shifts that distorts the kind of shape of the ion line and the reflection spectrum in general, there's also a time delay, right? Because the reflected photons take a longer path to get to us than the direct photons that we see in the power law continuum. So you get these lags. And the easiest way to model these lags is by making what's called the impulse response function. And that's what you see on the bottom left here, right? So we're going to simplify everything by saying, let's just model the rest frame reflection spectrum for illustration as a delta function ion line at 6.4 keV, and we can bring in the proper reflection spectrum later. And we're going to say, what happens if there's a delta function flash in the luminosity of the corona, such that at t equals 0, we see a delta function flash in the Comptonized spectrum. So there'll be a little bit of time where you don't see anything. And then the first reflected photons you see are the ones that are reflecting off the near inner side of the disk, because that's the shortest reflected path length possible. So this first ion line that you see is at a single energy because it's only 1 point, and there's no Doppler shifts because it's only transverse motion. You only have gravitational redshift. So the rest frame is 6.4, and this is brought down to below 6 here. And it obviously depends on the inner radius of the disk and all of these things. So a little bit later, there's this kind of front that's spreading out around the disk that depends on the inclination angle we're looking at. So a little bit later here, you see that you're now picking up some Doppler shifted parts of the disk, so the line gets broader. It gets broader still, and eventually you see the first photons that reflected off the back of the disk. Now, these come back particularly brightly because these rays are focused around the black hole, so you get a kind of high flux from the back of the disk, which again depends on the inclination and all of the other parameters. And then we're just seeing photons that reflected from progressively further and further out in the disk, so you're getting a narrower and dimmer ion line as you're going on. So this is what happens if you have a delta function flash in the luminosity of the corona. But what we really want to model is, what if the luminosity of the corona is going up and down in some quasi-random way as it is observed to do. We want to model how the reflection spectrum responds to that. So it turns out to be very easy to calculate that from the impulse response function, because it's just a linear problem. So it's a convolution in the time domain. So therefore it's a multiplication in the frequency domain. So we can use the impulse response function to make plots of time lag versus Fourier frequency, right? So you can say this is what is the time lag between the reflected emission and the total reflected emission and the total direct emission. And in order to do this, we're going to have to assume a mass, right? So on the left, if you see the x-axis is in mass scaled units, and if we want to get things in seconds and hertz on the right hand side, we have to put in a mass. So that's the first clue that this thing is going to be sensitive to black hole mass. If you also look on the y-axis on the left, the energy shifts are completely independent of black hole mass. So this is going to be where the kind of sensitivity to black hole mass comes in. The energy shifts only depend on distances or kind of size scales in the disk in units of gravitational radii, whereas the time scales depend on distances in kind of actual geometric units, like kilometers. Okay? So if we put in a mass equals 10 solar masses, we get for the low Fourier frequencies a time lag of about 2.2 milliseconds. And if we put that on this plot of the impulse response function, you see that basically at time equals 0, there's kind of the original flare in the corona. And then 2.2 seconds later, basically all of the reflected flux has been, because this part after 2.2 milliseconds is much dimmer than this part before 2.2 milliseconds. So it makes sense why you're getting this 2.2 milliseconds, but why does it go down with higher Fourier frequency? Well, if you're looking at higher Fourier frequency, you're basically picking out the faster variability timescales, right? So the kind of the faster fluctuations in the luminosity of the corona. So if you look at particularly fast fluctuations in the corona, those fast fluctuations are washed out in the reflected emission by destructive interference between rays that reflect off different parts of the accretion disk. Okay, so what ends up happening if you look at high enough Fourier frequencies, you're excluding rays that reflected off radii bigger than a certain value, and you're only looking at kind of the inner part of the disk. And the higher the Fourier frequency you're looking at, the further in the disk you're selecting to only look at. So that's why this keeps going down. And then eventually you hit this point where it starts going crazy, and this is phase wrapping, right? So basically this is when the reverberation lag becomes equal to the variability time scale itself, and you get hit with the phase ambiguity of Fourier transforms. It's pretty much exactly the same thing as if you're watching a movie and there's a car driving along in the movie and it looks like the wheels are going backwards on the car, and that's of course because the wheels have got nearly a whole rotation between snapshots of the camera. So each time it's getting nearly a whole rotation, so it looks like it's going backwards. And then you can imagine, so that's what this first fringe is here. Then you can imagine if the car speeds up a little bit more, you get to the point where the wheel gets just over a full rotation around between flashes of the camera. So then we're here. It looks like the wheel is going forward but slowly, and then you can make the car go even faster, and it gets nearly 2 rotations round between frames of the movie. So then it looks like it's going backwards again. So that's here, and so on and so forth. So this is going to come up. Okay, so because in our model we know what's reflection and we know what is direct emission, but if we want to compare this to the data, there's no labels on the data of which photons reflected off the disk and which photons were direct. The only way we can tell the difference between the reflected and the direct signals is that they have different spectra. The reflected has this reflection spectrum with an ion line and all sorts, and the continuum is just this power law with a high energy cutoff. Okay, so all you can do is look at the time lag between different energy bands. So you can look at the time lag in an energy band that has more reflection with an energy band that has less reflection. So 6.4 keV is the ion line, so this is reflection dominated, and 10 keV has very little reflection, so this is continuum dominated. And you see that you get a similar lag, but the size of the lag is diluted, right? And that's because both of the bands we're looking in have some reflection and some direct emission. 6.4 keV is reflection dominated, but there's some direct in there, and vice versa for the 10 keV. So you get this dilution, and you also get the kind of the fringes of the phase wrapping kind of smoother. Okay, so if we want to actually look for a kind of prediction of what this should look like in the data, the best thing to do is not, in my opinion, not just look at the lag versus frequency for 2 energy bands, but we actually want to look at the lag versus energy. So we want to make lots of these plots, each one with a different subject band frequency energy on the left, and the same, what I'm calling reference band energy on the right here. And then you can look at the value of the lag at a certain frequency and plot it against the energy of the subject band, right? So that's what this is. Oh, here we go. So this is the lag versus energy spectrum. And you can see that it has an ion line feature and a Compton-Hump feature. And this is exactly because at the ion line, a greater fraction of the photons are reflected. The reflected emission is lagging behind the direct emission. So this is for these parameters here. So this is calculated using the RelTrans model, and this is the original reference for that down here. It's a publicly available model. You can download it and play around with it. We're making the simplest possible assumption about the corona, that it's a point-like source, some height h gravitational radii above the black hole, and because then you can calculate everything exactly in general relativity, and we're working on making something better than that, of course. So can you see this in the data? Well, first of all, how do you try and calculate this in the data? Well, you basically just need to have light curves in many energy bands, and then to make one lag versus frequency spectrum, you need 2 energy bands, right? So you take the Fourier transform of one band, which we're going to call our reference band, 10 keV in the previous plot, and another one in a subject band. You take the Fourier transforms, multiply one by the conjugate of the other, you get the cross spectrum. The cross spectrum is a complex number. If you take the argument of that, that phase angle gives you the phase lag between these 2 energy bands, and then you can convert this into a time lag by dividing by 2 pi times the frequency. So you just need to do this, make many of these cross spectra, each time changing the subject band but keeping the reference band the same, and then you can make the observed version of the plot that I just showed you on the previous slide. So when you do this, you see that you do indeed see these features. You see it in AGN, and here's an example on the top. And we see it in at least one X-ray binary, but this on the bottom is by far the best example we have of X-ray binaries. So things to notice here, we are seeing this this line feature, and it's energy-wise, it's the same width in energy between the AGN and the X-ray binary, even though there's an enormous difference in mass. This is expected. The energy shifts don't care about the mass of the black hole. But if you look at the y-axis, the lags are about 1,000,000 times bigger for the AGN than they are for the X-ray binary. And that's because the AGN is about 1,000,000 times bigger because the black hole is about 1,000,000 times bigger. So you can also see that we're going to be able to get the mass out of this, right? Because just the size of the lag is linearly related to the mass itself. You also see that the frequency we're looking in is very different. This is again mass scaled, so basically things are bigger, everything moves slower in the AGN. So this is if you look at a kind of relatively high frequency for the system. If you look at a lower frequency, you see something that's completely different, right? So these are what we call continuum lags. These are nothing to do with reverberation, with the light crossing time scale. We instead think there's something to do with the spectral variability of the continuum itself. So we call them continuum lags. And if you again look at the y-axis, you see that these continuum lags are much, much bigger than the reverberation lags. So we're very confident that the reverberation lags are still in there at these low frequencies. They're just completely swamped by these much bigger continuum lags. And we even have evidence that I'll show you later that the reverberation lags are here, even in the continuum lags. So I wanted to kind of take a little bit of time out to understand this plot, because to some people it's difficult to understand how can you have different things happening on different Fourier frequencies. I did some simulations. So the red light curve is the soft energy band, and the blue light curve is the hard X-ray band. So basically if you look at only the long time scale variability, so the x-axis here goes from 0 to 1.5 times 10 to the 5 seconds, and you can clearly see that the hard x-rays are lagging behind the soft x-rays. There's a peak in the soft x-rays, then a peak in the hard x-rays. If you zoom in to part of this plot, so on the right is just a zoom in of the plot on the left, you'll see that there is that it's the other way around now. You see there's a peak in the hard X-ray flux here that is then a little bit later seen again in the soft X-ray flux. So that kind of that's the way to picture this. If you're going to a higher Fourier frequency, you're zooming in to smaller scales in the time domain. Okay, so basically there's kind of two ways to get around these continuum lags broadly. One way is to ignore the low frequencies altogether and just model the high frequencies. But I already showed you that the reverberation lag depends on frequency, and there's information in that, and there's actually really valuable information in that we want to exploit. So really we want to model all of the frequencies, and if we want to do that, we have to also have a model for the continuum lags that we include in our reverberation model. Right. So, and we want to model them out in the simplest way possible. That's the least computationally expensive way. So what we've been doing is we've been modeling these continuum lags as fluctuations in the power law index of the continuum spectrum. So this movie is obviously completely exaggerated. It's really tiny fluctuations that you need. But you can see that this would give hard lags because you have a peak in the soft X-rays, then you have a peak in the hard X-rays. And what we're doing is we're self-consistently accounting for the effect that this will have on the reflection spectrum. So if you change the power law index of the irradiating spectrum, you change the ionization balance. So you end up with a different reflection spectrum. These are two on the right. These are two different power law indices. And you see there's a very different strength of the ion line, for example. That's all in the model, and it's all in there with a first order Taylor expansion, which is easily accurate enough for what we need to do. Okay, so the first kind of outing of the model was from like the original paper, and this is we just fit the lag versus energy spectrum in one frequency range of the AGN Markarian 335. So we don't need to worry about the continuum lags for now. So basically the blue line here is our best fit. We see that there is this iron line feature in the data, and we're getting a good fit. So our best fit was 7 million solar masses for the mass of the black hole. And this is actually a good bit smaller than the other published black hole masses in the literature. Now, these two other masses, 26 and 14 million solar masses, they were obtained from much more mature technique, which is optical reverberation mapping. So, you know, we wanted to see what the difference was. So we fixed the mass to each of these two values and then ran the fit again. And we see that we actually get a decent fit even with these two masses. So what's going on? Why is this so degenerate with mass? Well, there's two things. First of all, there's an anti-correlation between mass and the height of the corona, and that's because the height of the corona is in units of Rg, right? So basically, the reverberation lag tells you the physical distance between the corona and the disk, and that can be only a few very large Rg, which would be over here, or it could be many very small Rg, which is over here. So that's the anti-correlation, but you also get these stripes in the chi-squared space here. So what are these stripes? Well, these stripes are phase wrapping, right? So for all of these solutions here, where you get a good fit for the dark colors, this is where there's no phase wrapping in the solution. And for this fit here, this is in the first phase wrapping order. This is the second phase wrapping order. This is the third phase wrapping order, and so on. So it turns out that our best fit that was showed by the green cross here, this is with no phase wrapping. And these two higher masses that we tried, these are in the first phase wrapping order. And there's nothing unphysical about that. These could, in principle, be decent solutions. There's nothing wrong with them. But there's very strong predictions about what should be happening in other frequency bands that we're not looking at, right? So here's now a lag versus frequency plot between a reflection and a continuum dominated band. And we're doing lag versus frequency for these three models again. So the blue line is our best fit, and we see that they're all the same in this gray frequency range where we were fitting the lag energy spectrum. But in the lower frequency range, there's an enormous difference. These higher masses are predicting absolutely huge reverberation lags in the lower Fourier frequency band, because they're only small in this band because they're phase wrapped. Okay, so if we look in this band, it should be easy to tell the difference, because these would really stick out like a sore thumb, and these will be buried beneath the continuum lags. So then we reanalyze the same data, but now it's Gulo leading the paper, and we're looking in two frequency bands. So we need the continuum lags in the lower frequency band, but the reverberation lags are still in there. So you get small reverberation features, and these reverberation features are now negative features because the reverberation lags are smaller than the continuum lags. So when you combine the two lags together, you end up with the reverberation lags diluting the continuum lags at the iron line. So you get a dip at the iron line instead of a peak. We're going to see that a couple of times. So when you do that, the degeneracies go away. We have only two frequencies. We're also fitting for the time average spectrum, by the way, to anchor the fit. And the degeneracies go away, and you have a nice bound on the black hole mass. You don't get the phase wrapping solutions anymore. So we're getting an even smaller mass now, 1 million solar masses. And this is a good bit away from the optical reverberation mass. And I don't know why. You know, it could be that our corona is too simple. We've just got this point source corona. You know, it could be, this is a narrow line safe at 1, which is that they're typically kind of around about Eddington ratio accretion, Eddington limit accretion. Our mass would put it at Eddington, and the optical reverberation mass puts it well below Eddington. But still, the optical is a much more mature technique than ours. Okay, so if you look in X-ray binaries, you actually get better data, so you can split into more frequency bands. So we looked at SIG-X1 in 10 frequency bands. The only downside is that we can't get to the very highest frequencies in the data that we used. So we're looking in only continuum lags dominated frequency bands. But we have this dip at the ion line, which comes from kind of the dilution, the fact that we've got reverberation lag and continuum lags in the signal. And we can also look at the modulus of the cross spectrum, which tells you about the variability amplitude. And basically what we're seeing here is that as you get to higher and higher Fourier frequencies, you're getting less and less variability in the ion line with respect to the continuum. And this is exactly what you expect in the model. And this is because the highest frequencies get washed out in the reflection spectrum by this destructive interference between rays that reflect off different parts of the disk. So when you put this all together, you get a mass contour. And it looks something like this. Oh, here we go. Yeah. So we were getting about 25 solar masses, and this was something that was freaking us out because our mass was too big with respect to the kind of the optical reverberation mass, not reverberation, the optical dynamical mass from 2011. But then it turns out there was a new optical mass published. There was a correction to the distance estimate to Cygnus X1, and it kind of brought the dynamical mass estimate up closer to ours, to 22. So this is an incredible success of the model, and it gives us some confidence to move forward. So because we're running a bit late, I'll skip forward with some stuff that's basically showing why it's good to measure the black hole mass with X-rays, because you can see you can do it for more objects than if it's for optical, and then it might solve some biases in the mass function. But I just want to skip on to thinking about how can this model be sensitive to the distance to the object and therefore sensitive to the Hubble constant when you're doing this with AGN. Well, this came about as we were putting more physics into the model. So basically, I said right at the start of this talk that the most important parameter that goes into the ionization calculation is the ionization parameters. This is the X-ray flux divided by the density of the disk. And for many years, partially as a kind of computational limitation and a storage limitation for grids, the disk density was always just fixed to this 10 to the 15 electrons per centimeter cubed value. And this is kind of what you'd expect from the simplest models to be reasonable for an AGN with a black hole mass of about 10 to the 8 solar masses, right? But then if you actually take the models and start playing with changing the density, you see that it makes a really big difference. So here's this paper from Garcia et al. 2016. He's basically held everything constant, including the ionization parameter, and then changed only the disk density. And you see that changing the disk density makes an enormous difference. The most obvious thing is this bump at the low energies, but there's also changes to the ion line here. And the way that you can, so the bump is easy to understand. So basically, some fraction of the flux that is irradiating the disk becomes thermalized in the disk. There are so many interactions between photons and electrons that it becomes quasi-thermalized. So this is a nearly black body bump. Obviously, it's not quite. There's many lines in here. But you can see this is nearly black body. So if you're holding the ionization parameter constant and increasing the density, that means you're increasing the irradiating flux. So if you're increasing the irradiating flux and the same fraction of the irradiating flux is thermalized, then you're also increasing the black body flux. And as you increase the black body flux, you increase the temperature. So this makes sense. The ion line stuff is a lot more complicated, but the point is that the density matters, right? You expect classically that from very simple calculations that the density of the disk is proportional to about 1 over the mass of the black hole. So this bump for AGN should be in UV, and for X-ray binaries should be in soft X-rays. And in the interest of time, I'm going to skip another couple of slides that are in themselves very interesting slides, but I want to get on to the final point. So the point is that if for years we only let the ionization parameter to be a free parameter, but now it turns out you can have the ionization parameter and the density free in the fit, and you constrain them both. So in other words, you can constrain, let's forget about the ionization parameter. You can constrain the irradiating X-ray flux and the density just from the shape of the X-ray spectrum. reflection spectrum.
Adam, sorry to interrupt you. So we can have 15 more minutes to. I mean, we can go more. I mean, up to 12, 15 or so. So no problem. Yeah, please go ahead.
Oh, okay. Well, I'll finish to this point, and then I'll see what we want to do after that. I just wanted to make sure I get to the kind of headline point of the talk. So thanks. So basically, if we can measure the irradiating X-ray flux, and we're doing X-ray reverberation mapping, so we're measuring the kind of physical size of the disk. That means we have a flux, we have an area, so we have a luminosity, right? So basically, hopefully you see where I'm going. We can use a model to measure what the luminosity of reflection is, and then we measure a reflected flux, so therefore we get the distance out of that, okay? It's a little bit more complicated than that, because this reflection spectrum isn't just emitting isotropically, it depends on the emission angle, but that's all in the model. It's all in the model, it's all predicted in the model. So basically, we realized that once we had the density as a free parameter, we had the density and the ionization parameter as free parameters. And we realized that from that, you could calculate the distance. So we basically realized that we were previously effectively marginalizing over the distance. We were having it was a nuisance parameter that we didn't care about. And what we really cared about was the density and the ionization parameter of the disk, which is of course nonsense. What we really care about is the distance and the density, and the ionization parameter is just some combination of other things that are more interesting. So now in the new version of the model, the distance and the density are model parameters. And the ionization parameter is something that you can work out from everything else if you want, but that's the thing that is marginalized over. So basically, there are many uses of this, and the kind of the obvious, most bog standard use is just, okay, well, if you've got X-ray binaries where you know the distance, then you can kind of have that as a prior in your calculation, and it gives you a better constraint on everything. But the most ambitious thing you can try and do with having the distance as a parameter is obviously try to measure the distance to AGN. And if you can measure the distance to AGN, you get an estimate of the Hubble constant, because it's very easy. We already have measurements, very accurate measurements for the redshift of these things. And you can only do this for nearby AGN, right? So, and it's particularly interesting to do that at the moment, because obviously there are these two very good ways of measuring the Hubble constant through either the distance ladder, the traditional distance ladder with Cepheid variables and type 1a supernovae, so that's in red, and modeling the cosmic microwave background, in particular the temperature anisotropies of the cosmic microwave background. And very famously at the moment, these two estimates have kind of diverged from each other as the error bars have got smaller. They're now more and more in tension with one another. So this is about 4.4 sigma level here. And of course, this is very interesting indeed, right? If the distance ladder measurement is correct, then there's something missing in the cosmological models that are being fit to the CMB, which would be really cool. So there's a lot of people trying to come up with new methods to measure the Hubble constant, and I want to use this as another new method to measure the Hubble constant. So the first thing that I did with this, the first thing that I've recently done, is basically just tried to work out, well, can we get the statistical precision required to be relevant in this argument, right? Because we are going to get an H0 measurement, but the error bars might be so enormous that that they're bigger than this whole plot here. So what I did was just simulate an AGN. So the simulation is based on Arcadian 564. So this is a bright nearby AGN, and it's kind of a typical XMM and new star exposure. So the green lines in the top plot are XMM, and that the two shades of blue are new star, the two modules FPMA and FPMB. So basically simulated the time average spectrum and the time lag versus energy in two frequency bands only for XMM. And then I fit the synthetic data back with the same model to see how accurately we can measure the distance and the mass and this kind of thing. So once you do that, you can run an MCMC. So in each step of the chain, you have a distance. So then from that, you can calculate the Hubble constant. So we know the redshift, and the accuracy of the redshift is so much better than everything else. There's no point taking into account that there is an error on this. We also need to include a peculiar velocity of the galaxy, right? Because the redshift we measure isn't just the Hubble flow, it's basically the velocity that the galaxy is moving away from us, and that's partly the Hubble flow, and it's partly just, you know, whichever direction the galaxy happens to be moving in locally. So we don't know that, of course, so I put that in as a Gaussian random variable, so with a mean of 0 and a standard deviation of 600 kilometers per second. So if you're looking at a redshift of 0.02, this peculiar velocity is about 10% of the Hubble flow peculiar velocity. So it's not negligible. You need to take it into account. And when you do that, you get these contours on H0 and on the mass as well, right? And this is the kind of joint contour on H0 and the mass. So to 3 sigma, we're getting a measurement that's something between about 40 and about 100 kilometers per second per megaparsec. So plus or minus 30 kilometers per second per megaparsec. So of course, this is an enormous error bar, and this is not going to add to the debate whatsoever, but this is only for one AGN. And you can do this for many AGN and beat the errors down. So if we do this for K AGN, then very back of the envelope calculation, the error bar on H0 for the K AGN just becomes the error bar for one AGN divided by root K. So then if we want to get down to an error bar of a 3 sigma error bar of about 6 kilometers per second per megaparsec, then we need about 25 AGN. And this is very doable. There are indeed 25 AGN with known reverberation features. And there are more probably with the signal to noise to be able to do this. So we kind of have the numbers to get the statistical errors. There's also an issue with flux calibration. X-ray telescopes are kind of notoriously bad kind of absolute flux calibration. So you measure the number of X-ray photons, but exactly how you convert that to the X-ray flux is not always well known. But NuSTAR happens to be the best calibrated of the current telescopes. And there's only about an estimated 4% systematic on the flux calibration. And this translates to a 2% systematic on the Hubble constant. And this turns out to not really hurt us with the accuracy that we're currently talking about. Okay, so that's really exciting. We have the statistical precision to, in principle, do this. Of course, going forward, if you want to actually do it, we need to address the systematics, and there are many systematics, of course, that I've kind of touched upon throughout the talk. So how do we address those systematics? Well, at the moment, we're trying to include more realistic coronal geometries in the code. I think that's the biggest problem, the biggest systematic in the method. So at the moment, we just have this lamppost model where we have a single compact corona. But eventually we want to have lots of different extended geometries in the code and see which one the data prefer. At the moment, we've only got to the point where we have 2 lampposts. But of course, once you have 2 lampposts, you turn that into n lampposts, and then they become surface area elements on a corona. So we want to include more realistic geometries. And the way, a good way to test this is to look at very high quality data from X-ray binaries, in particular ones where we know the mass and the distance already, because we can put the mass and distance in as Bayesian priors and then fit the model with different corona geometries and get out which one chi-squared prefers, basically. So that's one method of trying to work out the shape of this corona and then use that in future. Another really exciting prospect is X-ray polarimetry. So very soon, this is due for the 9th of December, IXPE is going to launch. And this is going to kind of really give us a new window on X-ray polarization. So this will hopefully give us the first ever solid detections of X-ray polarization. You know, this is in the 2 to 8 kV band. from X-ray binaries and AGNs. This gives us this extra lever handle on what the shape of the corona is. Put very simply, the more asymmetric the corona is, the more polarized its emission is, and that's what's shown in this figure on the right here. Basically, you get more polarization the flatter in one direction the corona is. You also need to account for general relativity, because a curved space-time rotates the polarization vector. So you can think of this as gravitational Faraday rotation. There's no material necessarily, it's just the gravitational field itself. So with IXPE, we are scheduled to look at AGN and X-ray binaries. We've got these two AGN in year 1 on the schedule. And we've also got these two X-ray binaries on the schedule in year 1. And also we'll look at transient X-ray binaries, you know, depending on if it's over a flux threshold. So that's very exciting. And then another systematic I want to talk about that's been on my mind a lot. The thing with addressing systematics or kind of improving the model, there's basically a kind of there's a weighting function, right, of which things you address first, and it's some balance between importance and doability. And the corona is kind of a difficult thing to solve, but it's very important, so it's towards the top of the list. And this is something that is quite important, but infinitely doable to solve. So this is also towards the top of the list. And it's basically that we need to remember that the incident spectrum has a low energy break. I've talked a lot about this high energy break, but there's also a low energy break. And at the moment, this is hardwired in the models to some value. It's a seed photon temperature of 0.05 keV. But actually, it really needs to be a free parameter, because where this low frequency break is in the dashed line really has a bearing on the shape of the reflection spectrum. So you could be measuring the wrong density and therefore the wrong distance. It's kind of easy to do this. It basically just needs the models to be ran again and make new bigger grids. So this is something that Javier is doing, but it takes months to run the model. So that is something that will be addressed in the future. So I'll leave my conclusions here, because we're at the hour. There are some things I didn't talk about, but I got through most of what I wanted to say. So I'll just leave my conclusions and take questions. Thank you very much.
Thanks a lot, Adam. It was really a fantastic talk, and we are kind of mesmerized. Okay, so now time for questions. Yes, we have 15 minutes for discussions. You may please unmute yourself and ask. Hello? Okay. There is, yeah, Vanisha, please go ahead.
Hi, Adam. Thanks for a great talk.
Thank you.
It's really interesting stuff. I just wanted to know, what is the kind of, limit in flux that you can do this with? You obviously need good statistics across the frequency range in the X-ray. So, so my background is X-ray binary. Sort of, what is the faintest one you've tried it with?
Yeah, so at the moment we're at the stage of taking the baddest, brightest objects we can and trying it on that. So we haven't really been pushing down to the lowest fluxes. So I don't really know. I don't have an estimate. We're just at the stage of trying this out on the brightest objects. In principle, you can stack, right? So with X-ray binaries, if you're only interested in the mass, for example, you could, in principle, do this for many objects and just have the mass tied between many observations of the same object and have the mass tied between all of the observations and get something out with better statistics there. it becomes very fiddly. If you're doing this with many spectra, you just kind of end up with kind of hundreds, thousands of spectra in X-spec, and it gets a bit difficult. But in principle, you could do that. But yeah, my answer is I don't really know, because we've only been looking at the brightest things so far.
Okay, great.
Okay.
Thank you.
So Andre, please unmute yourself and ask.
Adam,
Andre.
in retrans, there
Yeah.
are some very specific assumptions. You know, you take this pivoting power law and put phase in some way, and I somehow always had doubts how it relates to propagating fluctuations in an accretion disk. I mean, you mentioned that it may be lamppost irradiated by propagating soft photons, but this yet not been shown. So how much is an issue? How you feel this is an issue if you determine your parameters?
Yeah, I agree. It could be a huge issue, right? So basically, what Andre is saying is that we're trying to make this assumption about how you get the continuum lags, and we're doing it in the simplest way possible, and we're doing it in a way that kind of allows us to have this lamppost geometry, which makes everything computationally tractable. But maybe that's not the mechanism, right? Maybe there's an extended corona, and you have fluctuations in accretion rate propagating down that extended corona, in which case that might affect things a lot. My answer is I don't really know. I think we've got to try and have a bigger variety of things that we have coded up. I mean, and we also have clues about, you know, when we're measuring things, when we're fitting observations with the model, if we keep getting reasonable parameters, then we get a little bit more confident that what we're doing isn't crazy. So with SIG-X1, we're getting these this very reasonable mass. So that's very encouraging. So basically, I think the more compact the corona really is in reality, the more accurate our results are. The more extended it is in reality, the more wrong we are. And all we can do is just try different geometries and see how that changes things, and see which gives us a better fit. But you're absolutely right.
Okay, thanks, Adam. So I think you have already satisfied most of the attendees. So if we don't, I mean, anybody is not having questions, then I think people are hungry. So it's lunchtime here.
Ah, yes.
Yeah. So we can actually end this session, and thanks a lot. And it will be great if you can share your slides as well. So we will put that with the recorded video.
Yeah, sure. I'll send you them.
Okay. Thanks a lot, Adam.
Great.
Bye.
Thanks very much.